New chapter. Electric field. First definition of the chapter. Area of the region around a stationary charge in which a particle experiences force is called electric field. Now the question is, what is charge? It is defined as the product of electric current and time is called electric charge, because the formula Q is equal to I times T. Current is measured in ampere, time in second, so the charge is measured in coulomb. Now there are two types of the charges. One is the positive charge. It is defined as vacancy of electron or electrons in a substance is called positive charge. Vacancy of electrons in a substance is called positive charge. And the second is the negative charge. It is defined as excess of electron or electrons in a substance is called negative charge. Now, from these two definitions, it is clear that the charge carrier, either positive or negative, is just electron. So the charge carriers are electron. So positive charge is the vacancy of the electron, and the negative charge is the excess of electron. Now, the charge Q, that's why, is equal to number of electrons multiplied by charge of one electron. So Q is equal to N times E. E is the charge of one electron. Now, all charges are divided in two groups. The one is called the test charge. So the test charge is a small charged object which experiences force in the electric field. So a small charge particle which experiences force in the electric field is called test charge. It can be positive, it can be negative, but for the theory, it is assumed only positive charge. Both charges will experience force, but to clear the ambiguity, right, only the positive charge is considered as a test charge. Now, the second is a point charge. Point charge is the charge which exerts force on other particles in its electric field. Mean the charge which exerts force is the point charge, and the charge which experiences force is the test charge. Now, the point charge can be positive, it can be negative, but this test charge is assumed only for the positive charge. Okay, next, the topic is the types of electric field. Types of electric field. Now, there are two types of the field. Number one is the isolated electric field. Mean the field due to isolated charges. Isolated electric field due to single charge. So suppose we have a single charged object. This is suppose positively charged sapphire, and we have to draw its electric field. So first we will draw at least 6 lines equally spaced, must appear perpendicular to the surface. At least 6 in number, equally spaced. All feed lines are radial, mean they are spreading out. Now the gap between the two lines is representing the strength of field. Smaller the gap between the two lines, stronger the field, and greater the gap mean weak field. So this field is weak and this field is strong. So away from the charge, the gap is increasing. So away from the charge particle, electric field is decreasing. Now, there's a boundary of the electric field, and all points outside the boundary are considered infinity points. All points outside the electric field are called infinity. Okay, so these field lines are equally spaced at the surface, but gradually increasing their spacing. So the field is getting weaker away from the charged particle. Now, this is positive point charge. When a test charge is placed inside the electric field, it is repelled outward. So all feed lines are directed outward. So the positive charge has field which is directed outward. So the direction of the force experienced by the test charge, direction of the force experienced by the test charge in electric field is the direction of the electric field. Look, this force is directed outward, so the field lines are outward. And the line, this line is representing the path followed by the test charge after experiencing the force. Mean if the test charge is placed over here, it will move along this line. So the line is representing the path followed by the test charge after experiencing force in the field, and the gap between two lines is representing the strength of the electric field. Okay, thus, when a test charge is placed at the point A, and then it is placed at B. So this A will experience the large force and the B will experience a small force, because at the A, field is stronger as compared to B, which is called electric field strength. And electric field strength is a vector quantity. It is represented by capital E. It's a vector because it has direction. Now, the definition of the electric field strength is electric field strength is the electric force experienced per unit positive test charge in the electric field. So electric field strength is the electric force experienced per unit positive test charge, mean how much force is experienced by the test charge in the electric field. So the electric field strength, capital E, is the electric force F divided by test charge, positive Q. Now, force and electric field strength both are vector and both are parallel to each other. Both are vector. Now, the force is measured in Newton, charge in Coulomb. So the electric field strength is measured in Newton per Coulomb. Newton per Coulomb. Now, second, electric field. That is due to the negative isolated charge. Same, at least we have to draw 6 straight lines equally spaced at the surface of the charged sphere must appear almost perpendicular to the surface, and this is the boundary when a test charge, meaning the positive charge, is placed inside the field. It is attracted by the force inward. That's why this force is inward. So the field lines for the negative charge are directed inward. Okay, so all charges are kept by the surfaces. It means the surface is the start and the end of the electric field. So all electric field lines in the negative charge end at the surface, and in the positive charge, they start from the surface outward. So the all charges kept by the surfaces, but in the positive charge, they appear to be originated from the center. That's why we say that the charges are concentrated at the center. And here, all lines in this negative charge will meet exactly at the center, mean they will appear to meet each other at the center. This is just the assumption. So again, the evidence that the charges are concentrated at the center, but this is practically not true because the charges reside at the surface of the object, not inside. So all charges are kept by the surfaces. Okay, thus practically there is no field inside of the positive charge object and inside the negative charge object. So all charges are kept by the surfaces. So charge inside the sphere 0. That's why the electric field inside 0. No electric field inside the charged object. So electric field starts from the surface and it has maximum value at the surface. Now, the second type of the electric field, that is resultant electric field between two charges, like positive and negative, positive and positive, negative and negative. So we have to draw now the resultant electric field. For example, we have one sphere positively charged and the other sphere negatively charged. So electric fields are directed from positive to negative like this. So they are directed outward from the positive and inward negative. So this is the pattern of the electric field, resultant electric field between positive and negative. Look, at the surface of the positive charge, the field lines are close to each other. Similarly, at the surface of the negative charge, they are close to each other. So this is the strong field area. But here somewhere between the two charges, the middle of the two charges, the gap between the field line is large. So this dotted line is the area, is the point, or the points where the field is comparatively weaker than the surface. So this is first resultant field. Now move to the second one. Suppose two charges are similar, both are positive. Positive and positive repel each other. So the field will be repulsive. These charges will repel each other. So this is the pattern of the repulsive electric field. So field lines from the both charges outward. And this is neutral point, mean no electric field. When the charge is placed over here, it is neither attracted nor repelled because this is the neutral area. This is the neutral area. So similarly, we can draw resultant electric field for two negative charges. Again, repulsive. Same pattern for the two positive. The only difference of direction. So field lines are directed inward. This is the difference. And this point is again neutral point. No field, no force will be experienced by the object. So this is the resultant electric field. Now, move to this previous. When force is exerted in the field, force is experienced by the object in the electric field, some distance is covered by it along the force. Hence, when distance is covered in the direction of force, then work is said to be done. Then the work is done. So the work is done on the positive test charge. So work done per unit positive test charge in the electric field is called electric potential. So the work done per unit positive test charge in the electric field is called electric potential. Electric potential is represented by capital V, work by W, and charge by Q. So electric work is done, the work is done per unit positive test charge. So the work is measured in joule, charge in coulomb, and the joule per coulomb is volt. So the potential is measured in volt. Now work scalar, charge scalar. That's why the electric potential is scalar. It has no fixed direction, but for the positive charge, it will be considered positive. For the negative charge, it will be considered negative, just to remember the polarity of the charge. Okay, now this is the work done by the electric field, but the external body will do some work when the object is placed outside the electric field, when it is placed at the infinity. So this charge will not attract it because this infinity point is the out of the reach. So the better definition for the work done on the charge is, for the electric potential, is work done per unit positive test charge to move it from infinity to a point in the electric field is called electric potential. So this definition is acceptable in AS, but not in the A level. And this definition is acceptable for both AS and A level, P2 and P4. So it's better to remember this definition: work done per unit positive test charge to move it from infinity to a point in the electric field. Now come to this. Electric potential is the work done per unit charge. Now the work can be written as F into D divided by Q. Now F divided by Q is the electric field strength. So it is ED. Hence, E electric field strength is also equal to electric potential divided by D. E is equal to V divided by D. So V is measured in volt, D distance in meter. So there is another SI units for E, volt per meter. So there are two SI units for E. One is the Newton per coulomb, and the other is volt per meter. So either E is equal to F divided by Q, RE is equal to V divided by D. This first formula is usually used to calculate force, F is equal to EQ. And the second formula is used to measure the electric field strength between two parallel plates, one connected with a positive potential, other connected with a negative potential. So the majority of the electric field is uniform. So the lines are straight and parallel. So these field lines. And at the edge, there will be a non-uniform field pattern. But we usually, in calculation, we ignore it. So what is E between these two plates? This is actually the potential difference between these two potential divided by separation between the two plates. Now, in this area, the electric field is uniform. So when the graph is plotted between electric field strength and the distance, and the distance mean the distance of the point from any plate, mean the plates are fixed and we are changing the distance from the either plate. For example, first A point, then we move to B point, we move to C point. So the distance from the positive plate is increasing. Plates are stationary, plates are held stationary. So the spacing is constant. Then the graph is constant electric field strength. So do remember, this x-axis is the distance from the either plate. But if the graph is plotted between separation, mean the total distance between the plates, mean the distance between the plate is not fixed, it's increasing, then electric field strength is gradually decreasing because E is inversely proportional to separation when the same potential is provided to plates. So do remember, in this formula, E is equal to V divided by D. This is the potential difference between the two plates, and this D is not distance. This is the separation between the two plates. Now we have two plates which are held parallel and vertical. One connected with the positive, other connected with the negative. So majority of the field is electric field, uniform electric field. So field lines are equally spaced, and we are considering only the uniform portion, which is the major portion of the electric field. Now, these plates are separated with the distance d. Now, the positive plate is called anode, and the negative plate is called cathode. So cathode has excess of electrons and anode has vacancies of electrons. Now, when these plates, this pair of the plate is placed in sun due to the light, electrons will be emitted from the plate. So the emission of the electron from any cathode with the help of the light is called photoemission. Cathode has excess of the electrons. So when the light particle incident on the cathode, electrons are ejected from the plate. This is called photoemission. Similarly, if the pair of these plates are placed near any hot object, after absorbing heat energy, electrons are also ejected from the cathode. So the emission of the electron from the cathode with the help of the heat is called thermionic emission. So there will be two types of the emission, one due to the light, which is the photoemission, and other due to the heat energy, which is thermionic emission. So in both types of the emission, we will assume that the electron is ejected from the cathode with negligible initial speed, mean 0. And then after emission, it is attracted by the anode. Okay, so the initial speed of the ejected electron is 0. Now, due to the electric field, which is E is equal to V divided by T, we can calculate the force experienced by the electron. F is equal to EQ, and the charge of the electron is represented by small e, and its value will be given in the paper, 1.6 into 10 power minus 19 coulomb. So this is the force. Now, this force is, number one, attractive. Number two, it is constant due to constant electric field. And number three, it is accelerating force, mean resultant force. So the nature of the force is attractive, it's constant but accelerating. Hence, acceleration of the electron can be calculated by using formula F is equal to ma, or F is equal to A is equal to F over m, where F is the electric force calculated and m is the mass of electron. It will be given in the paper 9.11 10 power minus 31 kilogram. So now this acceleration is also calculated. Now the question is, what will be the velocity with which it hits the anode due to attraction? So V square minus U square is equal to 2AS linear kinematics equation. Initial speed 0. So V square is equal to 2 acceleration into S distance covered between the plates, and the final speed with which it hits the plate can be calculated by this formula, 2AD under root. Okay, so this. Now, force is experienced by electron. Distance is covered by electron. Hence, the work is done on the electron, which is converted into its kinetic energy. Now, work is equal to charge multiplied by voltage, and the kinetic energy is equal to half mv square. This is the charge of electron. So EV is the potential difference. So 1 by 2 mv square. So we can write 2 times EV over m is equal to speed square. So speed is also equal to 2ev over m under root. So this is another formula for the final speed of the electron. V is the electric potential between the plate, m is the mass of electron, E is the charge of electron. These two formula will give you the same answer. So from this formula, we can write the speed V depends on V only, because E constant, M constant, 2 constant. So V is directly proportional to under root potential V. So if V constant, then the speed final hitting the plate will be constant, will remain same. Okay, the last of this lecture. Now two plates are held parallel, one connected with a positive 16 volt, other connected with a negative 16 volt. Electron is ejected from the point A and it hits the anode at point B. Now, electron is ejected from the point C and it hits the anode at Q. The speed will be same because electric field strength at A exactly equal to electric field strength at C. Force experienced at A exactly equal to force experienced at C. So acceleration at A exactly acceleration at C. So the final speed at B exactly the final speed at D. So the electron ejected from A, electron ejected from C will hit the same, will hit the anode at B and D with the same speed, because all parameter, all physical quantities are same. But when these two plates are not parallel to each other, their potential is same, 16 volt minus 16 volt. One electron is ejected from A, other ejected from the C, right? Look, now the field is non-uniform. It is getting weaker gradually. It is non-uniform, no straight line, and at this point the field is strong, and at this point the field is weak. So this is weak both in strength and in spacing, right? So now when electron is ejected from A, it travels along this curved path, it hits the point B. C is the point, electron is ejected, it travels the plate at this point D. Now, when we will compare, the electric field strength at C is stronger than electric field strength at A. Force experienced by the electron at C is greater than the force experienced at A. Acceleration at A acceleration at C is greater than acceleration at A, but the final speed at C will be exactly equal to the final speed at A. The final speed of hitting at B exactly equal to the final speed of hitting at D. Reason we have done that the speed depends only on the potential difference. So the potential difference between A and B is 16 minus 16, 32. And the potential difference for C and D, again 16 minus 16, again 32. So it does not depend on the rest of the value. It depends only on the potential difference. So the potential difference for A and B, C and D is 32. So the same final speed on hitting the anode. Rest of the quantities are not equal.